Welcome again to the SMU WebEx session today, where we'll be speaking to you from the Industry Trends and Developments focus area on rapid technologies and additive manufacturing. We are going to go through a few housekeeping rules before we get started with our presentation. So for those of you that are already wondering if the information will be available after the session is over, the answer is yes. We will be recording the session, and that will be available for download. Our session will cover about 40 minutes of conversation, dialogue from our presenter, Greg Morris, and we will cover a Q&A session after the presentation and end with that. We have everybody that's called in your phone lines are muted right now, and they will be unmuted at the end of the session so we can have open dialogue with our presenter, Greg Morris. During the presentation, you can use the chat feature and ask questions along the way. For the Q&A session, we also have that the Q&A session so that you can log any questions that you'd like to have answered at the end of the session. So immediately following the session with Greg presenting, we will open those lines and get the conversation going. So we will. I'd like to move to present do the introduction of our keynote speaker this afternoon, Greg Morris, again with GE Aviation. He is our current Rapid Technologies and Additive Manufacturing Chair here at SME. He's been a member of SME since 2008. Greg's been involved with rapid prototyping and manufacturing industry since 1994, where he and two other partners started Morris Technologies. In 2007, Morris and his partner founded another company, Rapid Quality Manufacturing, to focus on the production of additive metal components aimed at the engineering, aerospace, medical, and other markets. In November of 2012, both companies were acquired by GE. In his new role with GE Aviation, Morris is responsible for helping to advance the knowledge of and application for additive manufacturing technologies throughout GE, and he works closely with the existing GE teams that have been working with the technologies. Morris has written several new articles related to additive manufacturing with specific emphasis on additive metals. He is presented in various trade shows, including several with SME, Aerospace Design, Aeromold, and several others. I would like to welcome you today to hear from our guest and keynote speaker, Greg Morris. Greg, take it away.
Okay, great. Thanks, Natalie. Just a real quick sound check. Natalie, if you can confirm that I'm on here.
Yes, you are.
Excellent. Okay. So good afternoon, everybody. For those who have joined or are joining, and welcome to this webinar. The intent here this afternoon is for me to review a little bit about our TAM and some industry trends in the rapid technology and additive manufacturing field. So this presentation I previously gave as an overview at SME's annual conference earlier this year. And to this audience, I think we have a variety of people that are joining today. Some are very experienced users, and I know a few of you, so welcome. And then for those who I don't know, or those who might be a little bit newer to the rapid technologies and the additive manufacturing 3D printing field, hopefully this broad overview is educational. But at the end of the day, I'd like to go through this presentation, hit at a very high level some of the trends that are happening today, and then allow for questions where I think ultimately we'll find more value in the specific questions that some of you might have in this topic area. So let me go ahead and proceed. Basically what we'll cover today will be the 3D imaging area, some nano manufacturing activity in additive and 3D printing around medical, the medical industry, some of the work that we're doing in education, and direct digital manufacturing. So these are the topical areas that the Rapid Technology Additive Manufacturing, or RTAM, technical community currently have as groups. So in that order, I will go ahead and run through these various topics. So the first topic is 3D imaging. Now, admittedly, this is not an area that I personally am technically involved in, but it is an area that's growing very quickly. And in fact, we have always looked at the 3D imaging market as being very closely linked to the 3D printing market. And I think we're seeing that convergence happen in a faster way as we move forward. There are a ton of different 3D imaging or scanning or measurement, metrology type of systems that are on the market today. And those can range from laser to white light to actual taking points on a surface from a CMM type of a machine. But what they share in common is having the capability to take either very small components or very large structures and digitally scan these things and digitally produce a file, and we can reproduce that file in a 3D form by printing it or milling it in a subtractive form or what have you. But there are many different makes. This list continues to grow every year. The capabilities of these technologies are increasing year by year, and of course, as one might expect, the costs for these systems have tended to come down over time. Some of the applications, there are a variety of these, but some of the industrial applications can range anywhere from the dental arena and the medical world, as you can see in some of the left-hand images. We also see this type of technology being used to scan large structures, buildings, or large objects, and they do this very efficiently, and again, we can reproduce those objects or those structures in a 3D printing form. And then we also see industrial uses of the technology where, or more of a human use of it, which can be scanning the human body or scanning models and then using those even in film and some other type of applications. Some of the business models of how this technology is being used. This is a company started by Direct Dimensions called ShapeShot, and here you get the gist of the idea where this booth of 3D scanning was set up, and so some folks came by the booth and got themselves scanned, and then in relatively short order thereafter, that model of their scan was printed, and that becomes a takeaway or a take-home for them. So here is a potential business model where you can take the public and actually, in a fun way, not necessarily a functional way, use 3D imaging to translate it into a physical object. So just, I guess, some high-level 3D scanning market observations. What we find is that the short-range industrial market seems to be relatively fragmented. The architectural, which you saw an image of that before, is in more the long-range scanning, if you will, so distance-wise is what that is referring to, seems to be expanding. And then the medical 3D imaging arena is growing very quickly. And again, the dental is a good example. So if we use that as an example to delve into a little bit deeper, if you go to the dentist and you ultimately need to have a coping or some other replacement, say a tooth replaced in your mouth, the old way of doing that used to be to get an impression made. So you would put the material into your mouth, bite down, and that would give the impression that the dentist would send out to have that component modeled. A lot of dental offices are now moving toward digitally scanning your mouth or scanning that area and then pushing that digital file either to an internal milling machine or out to some of the dental shops that would then potentially 3D print that coping or potentially use the traditional methodologies. But we're quickly going into the digital age, and that also holds for medical as well. Industrial CT scanners are clearly entering the market, and I think we'll start to see an acceleration of that. And then human body scanning is certainly an interesting topic. As you saw in that previous slide, this allows for Hollywood and for other more practical, or I should say industrial applications to be utilized. So if you think about 3D imaging or scanning the body, you can imagine how there might be many biomedical applications that could push forward. And then the consumer demand is really sort of an unknown still. So how successful can that business model be where you have that home 3D scanner, which they're relatively inexpensive. I believe Xbox had something that came out a few years ago. So will the home user, will the consumer begin to use 3D scanning? One can again imagine how you can take an object at home, scan it, and then print it on your home 3D printer. So again, the convergence between these two technologies will be fairly interesting as we march forward. And I think there still seems to be a relatively strong consumer interest in 3D faces for 3D printing. We'll see how that ultimately plays out as business models, but to date, that still seems to be something that catches the imagination in a variety of ways. If we switch to some of the work being done in the nano arena of RTAM, I've picked a specific slide, which is from a company based in, I believe, Austria called Nanoscribe. And as you'll notice in this particular slide, we have some very small structures, obviously on the nano scale, where we are printing these objects from a 3D file. So these are printed in very, very thin layers. You can begin to see the scale of what these are printed at. And the horse, for instance, in that picture, you can see what 2 microns is represented at. So this has a number of interesting applications. It's still relatively new and early in development, but many applications. Medical certainly has interest in miniaturized components and small components that can accurately and consistently be printed. To date, these are generally printed in polymer-type materials. RTAM and SME, for that matter, is heavily invested in education, and one of the programs that RTAM is involved in is the Bright Minds program. So for any of the folks on the call who have been to the Rapid shows, one of the days of the show, typically there are high school students that are escorted around the show floor and shown what new technologies and what manufacturing technologies are involved in. So a very successful program. It's one of the mission statements of SME is education. And certainly our young generation of students coming up, we want them to be very interested in the science and technology, engineering, mathematics. So SME spends, and RTAM in particular spends, a fair amount of time working with these students and getting them interested in the future of manufacturing for our country. We also have a tremendous amount of great work going on with the ASTM F42 Committee on Additive Manufacturing Technologies. And this has been a committee that has been in operation, I believe, for somewhere around 4 years. And there are many dedicated individuals within our industry that sit on this on a volunteer basis and develop and work on the various standards around additive manufacturing. As I'm sure everybody can appreciate, additive manufacturing is getting a tremendous amount of attention, and with any kind of new technology, there needs to be a mechanism that we can develop standards for quality reasons, for communication reasons, and that's what this committee is working on. So quite a bit of opportunity on this particular area, and for those who have interest, I highly recommend taking a look and getting involved in this type of a standard-setting community. I want to switch gears and talk just a little bit about some of the applications that we're seeing around the medical field. So we have a variety of pictures here, and I'll kind of go through some of these. So broadly speaking, what we see in particular with the additive metals arena is, and you see a number of pictures and photos that are additive metal components, is that we are leveraging these additive technologies to more efficiently and cost-effectively produce a variety of medical-type components. So on the dental example that I mentioned before, you can see the photos on the right, which one shows photos of dental copings that have been produced, and another photo of the laser in process of producing those same copings. So on this particular example, it's possible to get roughly around 400 to 450 of these individualized copings onto a build platform at one time. And typically these are one-day builds. So if you can imagine, you might have 400 to 450 customized individual customer copings on a platform at one time. And building in 24 hours, this particular example off an EOS DMLS machine, is able to allow us to see tremendous cost gains or a tremendous price point where if you compare this to traditional technologies, which would be casting those same components, the additive metal arena or the additive metal methodology is able to produce these components much more cost effectively and much faster. So back to the digital images or the capture that we get from the dentist office, you can in one day take that digital image, send it to a lab, and that lab can load it onto their machine and begin to build that coping. So the turnaround time to get those components back to the dentist and then to the patient's mouth are much reduced as well. So you have an overall much better patient experience due to the time you can turn it around, not to mention the cost savings. On some of the implant areas, you'll see a couple of images on the screen. One of them would be an acetabular cup, which typically is going into a hip replacement, a tibial tray, and also a knee implant. So what additive metals allows us to do is it allows us to build either customized or bespoke metal additive components for implants, and it also allows for us to have cost savings by putting very complex structures onto the implant itself. So in the pictures that show the acetabular cup and the tibial tray, what you'll see is a sponge-like appearance on that one surface, and that's the in-bone growth structure that is directly printed out of the machine. In both of these cases, those were produced off of an EOS DMLS machine, and those particular in-bone growth structures allow for the bone tissue to grow into the titanium, in this case, titanium metal structure. So you get a better bond between the human body and the implant that you're putting in, and you're able to save a substantial amount of cost in producing these components over the way that that is currently being done in the medical industry today. Other examples can range anywhere from mouth guards, as you can see from the photos with the little mouth guard that appears to be the British flag on it, to prosthetic devices, bionic type devices. There's a number of applications in the medical field for additive manufacturing, and the examples are increasing every day as to how various companies and individuals think about leveraging the technology. If we talk a little bit about the direct digital manufacturing group, and I'll focus in on polymers. So direct digital manufacturing is another way of saying additive manufacturing or 3D printing. There are a number of different terminologies used, but they all basically refer to the same area. In the polymers arena, we have a number of different mechanisms to produce a 3D part from that 3D CAD file. A few of these are on the screen. So we have the guitars, which are produced by Olaf Deagle out of New Zealand, and he is using a selective laser sintering technology to produce one is a hive guitar, the other one's a spider-oriented guitar. And these are each customizable guitars where Olaf is using his designing capabilities, love of music, and additive to actually produce a business model that has seen a tremendous amount of growth and traction. There are very functional applications as well. So if you look at the hand that's holding the apple and the little arm that's coming out, that arm that's coming out to grab the apple is a selective laser-centered component, which is a powder bed technology. That particular item has been custom designed using additive manufacturing in every step of the way. So what you don't see is where that gripper comes to the apple, those little gripping fingers actually will wrap around the apple. So it is a unique and novel way of leveraging additive to produce something that was based probably on an elephant trunk and is used in automation and industry. On the lower photo, you see an architectural model, again, that was produced out of the SLS process and very suited to that particular application because with the SLS technology and the powder bed technology and polymers, you generally don't need a support structure under some of your components and layers that you're building in. So in a very complex model such as that stadium, you have a number of undercuts and areas that do not require supports. You remove the powder after building, you can produce a very detailed model. From Stratasys, we have a variety of materials that are also very functional materials. So in those photos, you see probably these are fused deposition modeled or FDM modeled ABS components. And this works by a filament that is fed into a nozzle that's heated, and that nozzle lays the material down in the X and Y direction, and then layer by layer builds up. So you get models that you can print in different colors, as well as have a high degree of functionality. Ultem is another material that they use, and that has a higher temperature resistance, used in a variety of applications, aerospace included. On the lower left-hand sort of area of the screen, you'll notice what look like razor blades, and those are actually, or razor blade handles, I should say, and those are actually produced by a polyjet type of technology, where the technology utilizes a couple of different materials, and you can insert those cartridges into the machine. One could be a hard durometer, let's say. One could be a soft durometer. And combining them digitally, you can create in-between durometers. So you can have a very soft area, a very hard area, and at the end of the day, you can produce a component that has soft grip and also the hard plastic as part of it. So technology that is currently, that company was actually acquired by Stratasys, so that's now part of the Stratasys line of technology. If we look at metals and additive, we'll find that there are a number of developing applications. And so on the screen we have a variety of components that I'll quickly go through. They range from the stiletto heel that you see, which is obviously a fashion-oriented type of component. And then in the middle is really where the power of additive and 3D printing come together. And that's a titanium component, and it's got a very different structure on the inside. And you can see it's a lattice type structure. It's almost a bone-like structure. And so that particular structure is something that was automatically input into a software system developed by Within Labs. And instead of that being a block of material, and let's assume that this is an aviation component, instead of that being a block of material that has two passages at the top coming to one passage out the side, we've been able to, in this particular case, the example is showing the ability to lightweight that part. So you might reduce the weight on that component by 50%, 60%. In the world of aviation, if you can take a pound out of what you're flying, that has substantial cost savings and fuel across the life of that component, of that airframe, or of that engine. So the opportunities abound in the aviation world to leverage this kind of lattice structure. Of course, there are many other industries, whether they be for the sporting industry or consumer goods industry, where lightweighting is going to be a very important topic as well, medical as well. On the right-hand side, you'll see what are a grouping of high-pressure turbine blades. And I will pause to tell you that the industry is not using these in production engines. The technology is not capable of producing a high-pressure turbine blade, at least, that has the kind of demands that are required for such a component in the jet engine. However, for test engines and for prototype purposes, the technology is very capable of producing the geometry and also the mechanical properties that would be required to put into a test engine. Typically, test engines are only going to be needing to last for a couple hundred hours. The technology allows for these kind of components to survive that length of time with no problem. What's important here is that you can produce those kind of components out of a machine, one of the metal machines, and you can get incredible complexity on the inside, which you're not able to see in this picture, but it has a very complex internal structure. And you can basically produce those in a fraction of the time that it might normally take to cast the same component. So these are not what are normally single crystal blades in production. These are not single crystal metallurgically, but they are produced out of nickel-based alloys or other high-temperature alloys that have the mechanical properties to survive the extreme temperature and environment and RPMs that a test engine might see. Test engines typically are looking to get data, and for that purpose, this technology works very well. Those particular components were produced on a direct metal laser sintering machine. It's difficult to see, but the airflow, the cooling passages on the blade, all were grown in, so the shaped holes were grown in, and then there was post-finishing that took place on those blades. So the blade surface itself, the dovetail and getting the tighter tolerance, those were all post-machined or post-worked in some form or fashion. Other examples would be the center picture at the bottom, which is showing a heat exchanger. Again, that's a within labs design. In that particular example, you have a very complex set of passages that make for a very efficient heat exchanger. And there is quite a bit of interest in a variety of industries and looking to leverage additive and the complexity that you can build in with various materials that are being developed to create heat exchanger designs that are more efficient and perhaps even more shape conforming than what are currently out there today. Again, in the aerospace world, heat exchanger weight is an issue, and we're seeing that with additive we can reduce the weight substantially, yet maintaining or even exceeding the performance characteristics of certain components. So if we go to some of the other technologies that make up the additive world, on the upper left-hand side, appropriately enough today, we have a photo of something that was basically off of a home printer. So this is perhaps a bit whimsical, but you can envision having a home printer or buying those components off of one of the online websites, which I'll get to in a minute. So if you have a designer at home, or if you just wish to pull that design off of some of these online websites, you can make little components like this very quickly. Again, if you had a home printer, you could do it at your home, or you can order seamlessly offline on some of these online resources. In the middle, you see what looks like a cell phone, an iPhone, and you also see what looks like an orange. The components actually were produced by a technology called MCore, as well as the face on the bottom, and that's a paper-based technology. So in this particular example or this particular case, what we've got is a technology that's able to build layer by layer using 8.5 by 11 sheets of paper that you would go buy at Staples or any other office supply store. They use a binder layer by layer and a knife to cut out the two-dimensional shape for that layer, as well as making a grid pattern that you later remove. Because it's printing, you can print color, and that is why we have these very lifelike looking objects on the screen, including the face, which again, that was printed on the MCore system. It's a paper model that has been printed in color, and once again you're seeing that link back into the 3D scanning arena where that face was scanned. That's somebody's face that was scanned, and then that file was downloaded to the machine and printed out. On the left bottom, you'll see a kind of a novel-looking technology that is it's from a company called Wobbleworks. It's the 3Doodler, and this was a crowdsourced, crowdfunded component whereby I think they went out to try to solicit somewhere around $30,000 for their item, and ended up with something far exceeding that, over $1 million. That basically is a pin, if you will, that has a filament fed into the back of it. It's an ABS-like material, and as it's fed through, there's a nozzle at the tip, and you can see that on that left-hand picture, where it comes out, it's force-fed through, heated, and then as it comes out, it quickly cools. So you can actually create in 3 dimensions with your hand. I don't know the status of that today, but it is another application of 3D printing in a whole different way, where the user is actually moving the 3D printing mechanism around and the material around themselves. So if we look at some just high-level trends over the past year, clearly the attention in the industry is phenomenal. There is an incredible amount of press that is being given to 3D printing, to 3D scanning. I think we hear from almost every major news organization and magazine an article on 3D printing at some point in the last year. And I think we're also starting to, as a result of that, begin to get industry acceptance of these technologies as not just being fanciful or prototyping technologies, but we're starting to see the industries, the various industries, begin to look at these technologies as a means to production of components, and even end-use items, even consumer end-use items. And that goes for both the polymers and the metals. So, and honestly, I don't know if there's an industry that really hasn't been touched by these technologies at this point, or isn't looking at the technologies to see how it impacts their business. I think you can look at anything from medical and aerospace, energy, luxury goods, and on down the line, and it seems that the technology, whether it be in polymers or metals, is having a play in most of these industries. Look a little bit at the materials. Materials drive a lot of the applications, as might be expected with any of these prototyping technologies. So the photo of the violin being played is actually a PEEK material produced by EOS. That showed up on the cover of The Economist a year or two ago, and under the subtitle of Print Mea Stradivarius. So it's a very durable, high-strength, temperature-resistant material that's being produced in a modified SLS system that is sold by EOS. In the middle, again, as an example of high-pressure turbine blade, and the only reason we are able to use, even in a test engine, the metal components we do, which are high-pressure turbine blades, instrumentation probes, vanes, all kinds of different parts, is because the materials allow us to get there. So in the case of the high-pressure turbine blade, that's made out of a nickel-based alloy like Inco 718, and that allows us to get the temperature and withstand the stresses that are put onto a component such as that. The next picture over shows an Ultem part produced by the FDM system, and again, a very high-strength material with a high flame retardant and resistance. So there's a application, many applications that this particular technology will be leveraged against, many in the aerospace world, again, on airframe ducting and various components. It's a little tough to see, but there's a Petri dish shown. That's actually work being done by, in this particular case, Rice University, although many other universities, Cornell and others, are utilizing 3D printing to print bio components. And although we're in the early stages of where this technology is, there have been a variety of successes in producing components that are like a heart valve that actually are replacing, at least in animal studies, other mechanisms and methodologies. So although we're not at the point of printing organs and their complete organs or complete systems, the ultimate goal would be to be able to look at how can we leverage, utilize 3D printing to produce some very complex organs in the body. So the materials, again, I think as a broad statement, will drive the applications, and 3D printing, fortunately, is finding that there are a number of materials that are high-value, engineering-related materials that allow us to penetrate markets and applications. And in fact, if you look at metals, we find that the materials are better than cast, broadly speaking, more closely aligned with wrought-like properties. And that opens up a tremendous amount of applications that otherwise, if we didn't have those kind of material properties, we never would see the penetration of additive manufacturing like we do. I would follow by any of these materials that we're producing or that are made today and state that it is a very expensive proposition to qualify and to characterize these materials for a variety of applications. In the aerospace world and in many other industries, the material properties have to be known so that the engineers and designers can design to those properties. And it costs millions of dollars. It takes years in many cases to fully characterize and produce the curves that the engineers and designers can comfortably design to. In many of the industries that are leveraging and using this technology, risk is always an element that needs to be mitigated, and understanding the material properties in a more comprehensive way and fully allows for some of that risk to be mitigated. I think we're also starting to see a fairly large push of new business models and online web-based content. So the folks that you see on this screen have different business models, but in the end, They have a variety of online content that the consumer and even industrial users can log into and download files, have parts printed. You don't have to have a part or a printer in your house or even next door to be able to, or at your company to print something. Many of these websites cater to the individual who would like to get on and make something that's unique, or to select something that exists as a gift or what have you. So there are a number of online companies that are taking advantage of and pushing the digital content aspect of additive. And I think we're going to probably see a larger number get involved with different business models. It'll be interesting to see over the next couple of years how the companies that currently exist fare, as well as how some of the other business models that will be created turn out. Relative to some industry changes, I'll talk first about one that's relatively near and dear to myself, which is the acquisition of our companies, Morris Technologies and RQM, by GE Aviation that happened in November of last year. So obviously I can talk to that one. There are many other industry consolidation and acquisitions that have been happening. 3D Systems acquired majority share of Phoenix. Stratasys has been acquiring a few companies, MakerBot, etc. And I think that trend will continue. We're going to continue to see new businesses pop up and new ways of leveraging and using additive, aka the Wobbleworks. And then the online content like Shapeways, we'll continue to see many of those type of companies develop and move forward. I also would suggest that we'll see a variety of different machines and machine manufacturers evolve their technologies. As would be expected with any high technology industry, the machines and the processes continue to get better, more affordable, more accurate, and that is a trend that we will see happening over the next 5, 10, maybe perhaps even 20 years as the technologies evolve and move forward. I think we will see better materials and we'll see many more applications. As we look into the future, I would expect to see a tremendous amount of additional industry consolidation. So that can range from the service providers to the OEMs creating the equipment, the software creators, the material producers. We will start to see a tremendous amount of consolidation, and I also think we'll see new businesses or new players enter these markets. As I just mentioned, we're going to see the technology capabilities expand rapidly. I think we'll see many new business models. There are a lot of people thinking about how they can leverage and use 3D printing and 3D scanning. In a variety of markets, you can see where there are going to be market niches. So you might suggest that somebody becomes an expert in one particular industry. They build their business around that industry, not only with the additive portion of their business, but with some of the other technologies that help to vertically integrate them. I still think we're going to see a fair amount of application discovery, and for sure we will see market displacements. So that already has happened in the aerospace industry. That has happened where companies who may not have been aware or as knowledgeable about the technology have found a larger company invested in earlier in the technology displace some of their market. And they do that by virtue of creating and designing components that start to bleed into what their markets were, and then the IP ultimately gets owned by that larger OEM. So I think that this is both tremendous opportunity and potential threat to many companies, and it's probably important for most companies and businesses to have an understanding of the status of 3D printing and 3D scanning and what that means to their business. So with that, I will go ahead and end my part of the presentation and open the floor to questions that anybody might have. And thank you for those who joined. Thank you for listening in.
Okay, great. Thank you, Greg. This is Natalie Lowell, and I just wanted to make everybody aware that I have set the phones to unmute, so you'll be able to converse directly with Greg at this time. We do have some questions that came through while you were presenting. And the first one comes from Raul Verma, who is asking about possible research areas in the specifically in the 3D printing area.
So that's a bit open-ended. I apologize. I'm not sure exactly what the question's asking, but there are a number. I mean, there is a tremendous amount of research being done across not only the universities where one would expect research to be centered, but there are a number of national labs like Oak Ridge and Lawrence Livermore, and even America Makes, which is the new name for NAMI, is another area where research and R&D is being conducted. And of course the OEMs themselves, so not only the equipment manufacturers and the powder manufacturers, but also the end users, like a GE, for instance, where a tremendous amount of research is being done in collaboration with many of these other partners on the outside.
Okay, great. Hopefully that was enough information for the question there. Another question that came about the metal technologies. How big a part can you actually print in either the polymer technologies or metal technologies?
Yeah, so that's I didn't cover the specifics on that in the presentation. So the answer is a multifaceted one. So in the polymer arena, generally speaking, the size limitation is probably going to fit within a call it a 30-inch cube. There are some technologies that can print a quote-unquote unlimited length part. So I'm very broad brush in this answer by suggesting that it's in that 30-inch cube. But most of the technologies you'll see will fall within that rough size range for a single built component, and that goes for the polymers or the filament or the powder type of technology. And each manufacturer's technology bed will vary. On the metals, the same answer, except I would call that a little bit smaller build envelope. The largest powder bed system that's currently on the market that I'm aware of is about 630 millimeters by 500 millimeters by 400 millimeters in its depth. That's for powder bed technology. For powder fed or wire fed, you can print very large objects in the, say, 4 foot by 3 foot, 2 foot, or that kind of a range, or larger. And it just depends on what the structure is. You'll get different tolerances, different layer thicknesses, different detail resolution, different properties. So it really varies across the board as to what it is that the application is will drive what machine or what technology to use. But that's, broadly speaking, they're not parts the size of a house generally. They're going to be smaller components that stand or sit on a table.
Okay, great. And following up on that, Kevin Rooney has a question about the printing application and if you can actually print with stainless steel.
Yeah, you can print in stainless steel. So the stainless steels that we print in, for instance, would be the 17-4 alloy pH, and you can get different precipitation hardened results based on your thermal treatment. A 15-5 material, a 316L material, and conceptually there's really nothing that would prevent one from printing other stainless alloys or grades. Usually a new material has a development time associated with it to get the parameters dialed in so that you get the properties, the surface finish, the detail, and those type of components. So that isn't just a matter of pushing in say a 410 stainless into the machine and hitting the go button. You definitely have to dial in the laser or the electron beam parameters in order that you get the right mechanical properties, etc.
All right, awesome. Very good. Next question from Anad, who's asking about the new frontiers in additive manufacturing and wonders if you can speak on the electronic applications, specifically with respect to the materials.
Okay, so I'm not 100% sure I understand the question, but I'll try. So the materials, I'm not sure if that means qualification of materials or if that's referring to the variety of materials. I'll take it to mean the variety of materials. I think there are, that's a developing area. There are going to be some limits, as there are with any technology, as to what materials ultimately are available, but there are a number of opportunities with additive. If you look at the metals arena again, there are a relatively few number of alloys that have been qualified or that are capable of being used, simply because we haven't had enough time to develop the different parameters. But the future state would be that we have many more alloys that become alloys that can be used, qualified. I would also suggest that we will start to see more of the multiple alloys being used on a component, so gradiated materials and that type of thing.
And that's related to electronics applications?
Well, in the electronics field, okay, sorry, maybe I missed the question a little bit, but in the electronics field itself, there are some applications I'm aware of where it's being utilized. There's some work at universities. I believe Optimec has some work they're doing with circuits. So I think we'll start to see a little bit more of that pop up. It's not anything that I'm aware of that's too far down the road, but there is some very interesting and very substantial work being done by a few of the universities, such as University of Texas, El Paso, again, Optimec, and others that are doing work with printing for electronics. But I think we're still relatively early in on that. I think Cornell also is doing some work there.
Okay. The next question is related to the broader markets for the different technologies, and specifically the home 3D printer versus industrial machines. Can you tell us a little bit about the differences between those?
Yeah, so I think the obvious difference is the price range. So industrial systems can range from $500,000 to a couple $1 million, depending if you're in the polymers or the metals arena. The home printers are obviously a magnitude, order of magnitude less. You're talking typically anywhere from $1,000 to $10,000, depending on the type of machine you're looking for. But with that, you have limitations on the home machine that the industrial systems may not have. So your tolerances are not as tight. Your range of materials will probably be more limited. You're probably not going to see as good of a surface finish. Those are just some of the limitations. The speed at which they build is going to be much slower than an industrial system. And typically the home systems, well, as far as I know, the vast majority of them right now are polymer-based, so there isn't a metals equivalent to the industrial metal systems that are out there right now. So when I'm talking about the home printing machines, I'm talking about the polymer-based ones. And often, though, they serve a very good focus and purpose, so I think they've come a long way in the last couple, 3 years than where they used to be, say, even 5 years ago. But they're still, a home printer is not going to give you the same definition and the same mechanical properties that you might get off of a polymer industrial system.
All right, awesome. Kevin, another question from Kevin here is, you mentioned earlier there's some hype out in the field with the expansion of the 3D printing and the like, and getting a lot of press and publicity here. He's wondering what kind of myths or hype surrounding the additive manufacturing. What are those? What are the greatest prevailing myths, if you will, or hypes that are surrounding that technology that are circulating today? Can you speak to those, the myths that are out there today?
Yeah, it's a great question, and I'm not sure I'm going to be able to come up with all of them, but I think one of the myths that I commonly hear is that 3D printing is going to replace X, whatever X is, and so that could be it's going to replace CNC machining or castings. That's false. That's not going to happen, at least not in our lifetimes. I think another myth is that 3D printing can be used to replace anything that goes wrong in your house. While it may be true that I can grow a new handle for my microwave that I just ripped off and do it on my home printer, the reality is, I can tell you right now, my wife will never go for a non-stainless brushed looking component. So that green plastic part I put up there probably won't last very long. She'll rip it off and order the real part. So, you know, I think there are going to be pockets of applications that one can use the technology for at home, but it's not going to be the replacement for every part that breaks or for every aesthetic part that goes that needs to be replaced on a you know, home appliance or something of that nature. Those are just a few. There are many. 3D printing is not a replacement for all manufacturing methodologies either. It's a tool, like any other tool, like any other technology. It needs to be used appropriately, and it should not, generally speaking, be used to do something that it's not meant to do. So, you know, we don't take a screwdriver and hammer a nail with it. We take a hammer, same analogy.
You might be there a while. No, it's over too, and I'm about ready.
So I did see a question, and I apologize. I see a lot of questions kind of coming in on the chat area, and let me just try to answer a few of those. One was, has hipping been considered to reduce porosity of metal printing, or is the reduction too great? Great question. By and large, and again, broad brush answer, parts coming off of the metal systems are 99 point some high % dense. So we have and have been for quite some time using HIP to more, I think, as partly to affect some of the properties of some of the alloys, sometimes used as an insurance against any potential porosity that could be present. But I will tell you that there is no reduction, or if it is, it's negligible reduction to the part. We don't have high porosity parts coming off of these machines. They're very dense when they come off the machine. All the metal parts, I didn't really touch on this before, but pretty much all of the metal parts in the systems today will need to go through some form of post-thermal treatment. Depends on the application, but again, broad brush, most of them go through some post-thermal treatment, which can be stress relieving, hipping solution, heat treating, annealing, etc. So there's a fair amount of that. Let's see here. I see a few more up here. Let me try to read one. Let's see here. What about the use of technology for making complex molds for casting? Yes, there are a number of mechanisms to get to a complex mold. So again, you can either create that directly out of some of these machines. Let's take some of the EOS technology that produces a sand part, typically used for complex sand casting cores. There are machines that can make the tooling to shoot the wax. The SLA technology, for instance, to make quick cast patterns, the SLS technology to make patterns that you can directly cast. So there are a number of mechanisms to make castings and complex castings using the technology. And to make the complex molds, you can also use these technologies in a variety of ways to do that. So that will be very part dependent, material dependent, and application dependent. Okay, so another question, this new business model, let's see here, would focus on empowering people to be able to build, assemble, modify, and create their own rapid prototyping machines. I think that's a follow-on to another comment that was made. There is that potential. I think people do kind of open source some of these machines. I think that will happen. It's not happening on a grand scale, but for those who are technically inclined, I think there are those type of things that are taking place. Here we go. Here's a good question. Do you envision any more acquisitions happening with other vendors, manufacturers by industries, aka GE with Morris? Yeah, I do. I think that's going to be the case. I think that's going to happen. We're in an interesting period of time where a lot of manufacturers, OEMs, are looking at the technology. They're looking at what they're doing in the technology or not doing in the technology. And they're trying to decide, how do they proceed forward? Do they greenfield? Do they go out and acquire? And I think, frankly, right now we have a situation where the supply base for a variety of industries is not really existing, or if it does exist, it's very small. So that sets up for a lot of potential acquisition activity, and I think we'll see that accelerate as we go forward. Let's see here. What CAD format is typically used? Well, there's two. The STL file has traditionally been used for 3D printing. but the AMF file format is something that's been talked about the last few years and is coming out, so I think we'll see more of that. And as far as accepting G codes or something that's more familiar to the CNC world, yeah, no, generally speaking, you start with the 3D CAD model, convert that into an STL or AMF format, slice the file, and then download that to the machine. All right, let's see. Carl Decker's got a great question of what's the opinion of development of the U.S. in comparison to the rest of the world, for instance, the EU, China, South Africa, etc. So as it relates broadly to additive manufacturing, I would tell you that all of those areas are active, Africa being perhaps the least active, although South Africa seems to be doing quite a bit of work in additive. But China, Asia is very active. China in particular has been investing a tremendous amount of partnerships with government as well as private industry to accelerate their footprint in the additive world. Europe has consistently been at the forefront of additive. A lot of the, almost all of the powder bed manufacturers, in fact, I think all the laser powder bed manufacturers exist in Europe, at least the ones that we're most familiar with. So Germany and Sweden, the UK, France, these are the active countries in not only pursuing the technology from an OEM standpoint, but leveraging it, using it in industry. They also get quite a bit of government collaboration and cooperation and funds. The U.S. has less government funding. That's recently changed with America Makes. I think that yet to be determined what exactly their mission and niche is. I mean, we know what the mission is, but how widespread will that be, and will that be truly an incubator for industry? But the U.S. is very active and still, I think, is in the lead relative to number of machines installed and how we use the technology. Okay. Let's see, what is typical tolerance of metal parts by the additive method? So that's another good question, and it depends on the technology. So that's a common answer, it depends. But on the powder-based systems, I think it's fair to say plus or minus 5 thousandths across a 10-inch bed is probably a relatively good answer. When you get into the larger structures and the larger machines where you're talking multiple feet, the thicker layers, obviously that tolerance is going to increase substantially. Feature definition can get down as small as around 10 thousandths of an inch. Layer thickness, 20 microns to 100 microns is the typical layer thickness in the powder bed systems, laser-based systems, as well as EBM systems. All right.
There's, Greg, there's one long, lengthy question from McGill. Basically, he's asking about the business model and having a young child. He gives the example of a 10-year-old boy trying to create a part on his 3D printer and then being able to, do that in his home. And there are shops that are already in place to do this. He mentions Tech Shop and MakerBot in New York. He's just asking about this business model and what you see happening with that kind of a model.
I don't, it would be an opinion only of mine. I don't have a good answer for that. Yeah, I think that's has yet to be fully addressed, perhaps. So if you order something online, it gets sent to your home. Who's nearby to be able to help you put that together? I'd say right now it's a collection of online enthusiasts that you would tap into, not necessarily a bricks and mortar store that you would go to. And unlike going to, say, the Apple store and bringing in your computer and having them walk you through it. I don't think that exists in any way, shape, or form, except in very specific locations at this point in time. Hopefully that answered the question.
Okay. Well, I think we're at the end of our time slot here. We appreciate everyone joining us today. We had quite a good length of questions there. Just as a reminder to close out, we will be sending out the link so you can download and review the presentation again at a later point in time. One call out I would like to make is that the SME will be on full display with our Rapid event coming up in 2014, and that will be held in Detroit at the Cobo Hall, June 9th through the 12th. We're currently looking for people to present at the conference, and we're recruiting abstracts right now until December 1st, and you can access that, the link on our website at sme.org/rapid. Greg and many of the members that are leading the Rapid and Technologies Additive Manufacturing community here at SME are fully engaged in helping us continue to bring the products and services and the educational formats to the forefront in events such as the one here in 2014. I'd like to say thank you for your work today presenting Greg Morris on behalf of GE Aviation and the SME organization, and we look forward to having you speak with us and our members in the audience again in the near future.
Great. Thank you, Natalie.
Thank you.